What happens when the reliable rules of reality simply stop applying? We tend to view the universe as a clockwork mechanism, predictable and steady, but in the deep stretches between stars, that order sometimes breaks down. We are looking for the anomalies, regions where gravity warps light into unrecognizable shapes and time seems to lose its meaning. These aren't just abstract mathematical theories, they are physical realities waiting to be understood. If this quiet investigation into the unknown resonates with you, a gentle like and subscribe supports the journey. This is Fall Asleep with Science. When you're ready, we'll begin our observation of the universe's strangest phenomena. The universe is a vast and mysterious expanse, filled with wonders that often stretch the limits of our current understanding. Beyond the stars and galaxies visible to the naked eye, there are phenomena so strange and baffling that they seem to challenge the very laws of physics we rely upon. As we move through the cosmos, we encounter occurrences that defy easy explanation, ranging from planets that appear to ignore the rules of gravity to stars that seem to manipulate the flow of time. We find vast, empty voids where nothing seems to exist, and fleeting moments too brief to measure accurately. The cosmos is full of these strange phenomena, and while science has solved many riddles, some remain persistent mysteries. One of the most intriguing puzzles in modern astronomy centers on a bright star named Fomalhaut, located approximately 25 light-years away from Earth. This is relatively close in cosmic terms, making it a prime target for observation. In the year 2008, astronomers using the Hubble Space Telescope announced a remarkable discovery orbiting this star. They identified a small point of light moving within the dusty debris ring surrounding Fomalhaut. This was not just an ordinary detection. It was heralded as one of the first exoplanets ever found via direct imaging. To understand the significance of this, we must look at how astronomers usually find planets. Typically, planets are detected indirectly. Scientists watch for the wobble of a star caused by a planet's gravity, or they measure the tiny dip in brightness when a planet passes in front of its star. Direct imaging is different. It involves blocking the overwhelming glare of the star to take an actual picture of the faint planet orbiting it. It is like trying to spot a firefly hovering next to a lighthouse beam from miles away. The object discovered in 2008 was named Fomalhaut B, and its discovery was celebrated as a major milestone in our ability to study worlds beyond our solar system. However, the story of Fomalhaut B did not follow the expected path. In the years following its discovery, astronomers continued to monitor the system, expecting to track the planet's orbit and analyze its atmosphere. Instead, they witnessed something baffling. The bright spot that was Fomalhaut B began to fade. It did not just dim slightly, it gradually became less and less distinct until by 2014, it was no longer detectable. The planet had effectively vanished. This disappearance presented a significant problem for scientists. A massive planet, large enough to be seen across 25 light-years of space, cannot simply cease to exist in the span of a few years. Planetary bodies are stable structures, built to last for billions of years. The vanishing act forced researchers to reevaluate everything they thought they knew about this object. Some began to question whether Fomalhaut B had ever been a planet at all. The possibility arose that the original detection was a misinterpretation of the data, or perhaps the object was something far more transient than a solid world. As scientists scrutinized the archival data and gathered new observations, the situation became increasingly uncertain. A leading theory emerged to explain this anomaly. It suggests that Fomalhaut B was never a cohesive planet. Instead, What astronomers likely saw was the aftermath of a colossal collision between two large, icy bodies, comets or planetesimals orbiting the star. In this scenario, the two objects smashed into each other with tremendous force, shattering completely. This impact would have generated a massive, expanding cloud of fine dust and ice particles. When first observed in 2008, this cloud was dense and compact, reflecting enough starlight to appear as a single, bright point mimicking the appearance of a planet. However, unlike a solid planet held together by its own gravity, a dust cloud is subject to the forces of its environment. Over time, the radiation pressure from the star Fomalhaut would have pushed against the dust grains, causing the cloud to expand and disperse into space. As the cloud grew larger, the dust became more spread out. The density dropped, and the amount of light it reflected decreased significantly. Eventually, the cloud became too thin to be detected by our telescopes, creating the illusion that the planet had vanished. According to this model, Fomalhaut B was not a world that died, but the debris from a cosmic accident that we happened to catch at exactly the right moment. If this theory holds true, it means we witnessed a rare and violent event in the evolution of a planetary system, rather than the stable orbit of a mature planet. Yet, this explanation, while physically plausible, does not satisfy every question. Debate continues regarding the nature of the collision and the exact composition of the debris. Could a dust cloud really maintain a planet-like appearance for as long as it did before dissipating? Some researchers have speculated on even more dramatic possibilities. Perhaps Fomalhaut B was a real planet that was destroyed in a cataclysmic event, torn apart by gravitational forces or a massive impact that pulverized it entirely. If a solid world were shattered, the resulting debris would indeed disperse rapidly, matching the observations of its disappearance. Others suggest that the fault lies in our instruments and interpretation. Observing distant exoplanets is an incredibly complex process involving the separation of faint signals from background noise. The data we receive is often fragmentary, consisting of a few pixels of light on a sensor. It is possible that what we interpreted as a planet was a transient phenomenon, a dense knot of gas, or a storm within the star's debris disk that happened to look like a planet during the initial observations. As our technology improves and telescopes become more sensitive, we may eventually uncover the true nature of what was seen. This specific case leads us to a broader reflection on the nature of astronomical study. Does the universe deliberately hide its truths, or are we simply misinterpreting the fragments we can observe? In the case of Fomalhaut B, we are left with a partial understanding. We saw something real, but the identity of that object remains ambiguous. The universe is vast and complex, often revealing itself to us only in pieces. It is up to scientists to assemble these pieces into a coherent picture. But the universe is not always forthcoming with clear answers. Astronomers must rely on data gathered from distant points of light, inferring the existence of planets, stars, and other phenomena from subtle cues. It is a task that requires not only technological precision but also great interpretative skill. The story of Fomalhaut B serves as a reminder of the limits of human knowledge. Despite our best efforts and most advanced tools, the cosmos continues to surprise us. Planets that disappear, signals that defy explanation, and phenomena that vanish without a clear cause all highlight the complexities we face. The disappearance of this object can be seen as a metaphor for our broader quest to understand the universe. We catch glimpses of the truth, but that truth is often fleeting, hidden behind layers of uncertainty. As we peer deeper into space, we uncover new information, but each discovery seems to raise more questions than it answers. Is the universe elusive, Or are we simply not yet equipped to grasp its full reality? Even if we never fully solve the mystery of Fomalhaut B, the search for answers pushes the boundaries of our knowledge. Each puzzle we encounter refines our models and sharpens our understanding of how planetary systems evolve. From the vanishing of a small object within a solar system, we turn our attention to a mystery on a much grander scale. A mystery involving an entire galaxy. In the year 2016, astronomers studying the Coma Cluster, a massive gathering of galaxies, made a discovery that added another layer of complexity to our map of the universe. They identified a galaxy named Dragonfly 44. At first glance, Dragonfly 44 seemed unremarkable, but upon closer inspection, it was found to behave unlike any other galaxy previously studied. The extraordinary nature of Dragonfly 44 lies in its composition. When we look at a typical galaxy, like our own Milky Way, we see a structure defined by its visible components: billions of stars, vast clouds of glowing gas, and lanes of dust. These elements make up a significant portion of the galaxy's mass and give it its shape and brightness. However, Dragonfly 44 defies this standard model. Observations revealed that almost none of its mass is made up of these usual components. In fact, calculations suggest that less than 0.1% of this galaxy's mass consists of visible matter like stars and gas. The rest, a staggering 99.99%, appears to be made of dark matter. Dark matter is an invisible and elusive substance that has perplexed scientists for decades. As far as we know, it does not emit, absorb, or reflect light, making it impossible to detect directly through traditional telescopes. We cannot see it, photograph it, or measure its temperature. It is a mysterious form of matter that we infer solely from the gravitational effect it has on the visible objects around it. We know it must exist because the gravitational pull we observe in galaxies is far stronger than what the visible matter alone could produce. If galaxies relied only on the gravity of their stars and gas, they would fly apart. Their rotation speeds are too fast for the visible mass to hold them together. Something unseen provides the extra gravity needed to bind them. That unseen scaffold is what we call dark matter. Dragonfly 44 is an extreme example of this phenomenon. Unlike most galaxies, which have dense, bright cores and well-defined spiral arms filled with stars, Dragonfly 44 is incredibly faint. It has very few stars, and its light is so dim that to the naked eye, if we could see it, it would appear almost as a mere shadow or a smudge against the black backdrop of space. Despite this ghostly appearance, the galaxy behaves dynamically, as though it is massive. It is held together by an enormous amount of gravitational force, far more than can be accounted for by its sparse population of stars. The only explanation that fits the data is that the vast majority of its mass comes from a massive halo of dark matter. This discovery has forced astronomers to reconsider their assumptions about how galaxies form. In standard models, the gravitational pull of visible matter gas collapsing to form stars plays a central role in giving a galaxy its structure. But in Dragonfly 44, with so few stars available, the visible matter is negligible. It is unclear how the galaxy maintains its integrity unless the dark matter is playing an unusually central role. Here, the dark matter is not just a hidden background helper. It appears to be the primary framework, preventing the galaxy from dispersing into the void. The existence of Dragonfly 44 suggests that dark matter may be more than just a component of the universe. In some cases, it may be the dominant architect. If a galaxy can exist with almost no visible matter, it implies that dark matter is an active, fundamental component in galaxy formation. This challenges the traditional view where stars and gas are the main drivers of a galaxy's evolution. With Dragonfly 44, dark matter seems to have taken on that role almost entirely by itself. Yet, despite its importance, dark matter remains a profound mystery. We do not know what particle it is made of, and so far, it has eluded every attempt to directly detect it in a laboratory. We know that it must interact with regular matter through gravity, but beyond that single interaction, its properties remain unknown. Galaxies like Dragonfly 44 remind us of how much we have yet to learn about the architecture of the cosmos. It is as though we are observing the universe through a thick fog, only catching glimpses of the underlying structure, while much of the true nature of reality remains obscured from our view. The discovery of such a galaxy sparks profound philosophical questions about the nature of the universe and the limits of human understanding. For centuries, astronomy has operated under the assumption that the visible elements, stars, planets, gas clouds, and galaxies were the primary components of cosmic structure. We built our models based on what radiated light, but Dragonfly 44 suggests that the visible universe may be only a tiny fraction of the full picture, a mere veneer over a much vast, darker reality. If dark matter can create and sustain entire galaxies with almost no contribution from visible matter, we must ask, how much of the universe's true architecture are we missing? Are there other forces at play that we have yet to discover? Does dark matter itself hold secrets that could reshape our understanding of existence? Some scientists speculate that dark matter could be connected to other unsolved mysteries in physics, such as the fundamental nature of gravity or the origins of the universe immediately following the Big Bang. If we can one day understand what dark matter is made of, it might offer answers to questions that have eluded us for centuries. Yet for now, Dragonfly 44 stands as a silent enigma, a galaxy that defies our expectations and challenges our comprehension of the cosmos. The name Dragonfly 44 is fitting in its own way. Like a dragonfly, it appears delicate and elusive, almost invisible against the grand scheme of the universe. Yet, it is bound together by forces we cannot see but must acknowledge. It serves as a potent reminder that the universe is far more complex than it appears to our eyes and sensors, and that we are only beginning to peel back the layers of the unknown. Dark matter, once considered a marginal correction factor in our equations, is now seen as a potential key to understanding the very fabric of reality. This realization leads us to reconsider the concept of emptiness itself. In space, where the human eye perceives only a void, lies a hidden reality far stranger than we can imagine. What seems to be silence and nothingness, even in the most desolate corners of the universe between galaxies, is not actually empty at all. It is a space brimming with constant, frenetic activity. Although it remains invisible to us without the aid of high-level mathematics and indirect observation, this phenomenon is a product of quantum theory, the branch of physics that describes the universe at its most fundamental, subatomic level. What it reveals is both mind-boggling and humbling. The notion that even in a perfect vacuum where there is supposedly nothing, something is happening, challenges our intuition. These events are known as quantum fluctuations. They are tiny, momentary changes in energy that occur even in what we call empty space. These fluctuations are not merely theoretical constructs or mathematical errors. They are real physical events. However, they happen on a scale so small and so brief that they defy everyday understanding. According to quantum mechanics, particles, some so small they cannot be seen or detected by current technology, appear and vanish in the blink of an eye. This is often described as pairs of particles and antiparticles borrowing energy from the vacuum to exist for a fraction of a nanosecond before colliding and annihilating each other, returning that energy to the void. They flicker into existence, last for an instant, and then disappear again. It is a strange concept to grasp. After all, common sense dictates that matter cannot simply emerge from nothing and then vanish. But quantum physics does not operate by the rules we observe in the macroscopic world around us. On this microscopic level, uncertainty reigns supreme. The particles that briefly appear in these quantum fluctuations do not obey the familiar, deterministic laws of Newtonian physics that govern falling apples or orbiting planets. Instead, they exist in a world of probabilities, where things can happen without an apparent cause or origin. This peculiar activity has led scientists to describe space, even in a vacuum, as something that is far from empty. It is more accurately described as a quantum foam, a bubbling pot of potential where particles pop into and out of existence in ways that are unpredictable and seemingly random. These fluctuations, though fleeting, have real effects on the physical world. They generate small bursts of energy. While an individual burst is so minute that detecting it requires the most advanced equipment and highly sensitive experiments, collectively, they hold the potential to influence much larger events in the universe. Some scientists propose that these tiny fluctuations may even help explain why the universe is expanding. For decades, researchers have puzzled over the mysterious force known as dark energy, which is believed to drive the accelerated expansion of the universe. Quantum fluctuations could, in theory, contribute to this force, providing the small outward pushes needed to propel galaxies away from each other over cosmic timescales. It is an idea that remains under active exploration, but the possibility exists that the vast expansion of the cosmos has its roots in these microscopic quantum hiccups happening all around us. Even more astonishing is the idea that quantum fluctuations might give rise to entire universes. This brings us into the realm of speculative physics and cosmology, but it is a concept that some leading scientists take seriously. In a multiverse theory, where our universe is just one of many, new universes could be constantly born from these fluctuations. The idea suggests that in the vast, empty space beyond our observable universe, quantum activity could eventually spark the creation of entirely new realms, complete with their own stars, galaxies, and even unique laws of physics. The notion that something could come from nothing is deeply counterintuitive. Yet, quantum fluctuations force us to reconsider our assumptions about what nothing really means. In classical terms, nothingness implies the absence of everything. No matter, no energy, no space, no time. But quantum physics shows us that even in the absence of matter and energy, space itself has an underlying structure. The fabric of space-time is not flat or inert, but filled with potential, always on the verge of bringing forth new particles and energy bursts. This raises a philosophical question, as old as human curiosity itself. Can something truly come from nothing? Quantum fluctuations seem to suggest that the answer is yes, at least on the smallest scale. But this leads to an even more profound inquiry. Is nothingness itself an illusion? If even the most empty parts of the universe are active, teeming with energy and particles that appear out of nowhere, then perhaps the very concept of absolute emptiness is flawed. Perhaps what we consider to be nothing is, in fact, filled with the seeds of creation. The implications of this question extend beyond science and into the realm of philosophy and metaphysics. For centuries, thinkers have debated the nature of existence and whether it is possible for something to arise from pure nothingness. Quantum fluctuations provide a glimpse into a reality where this may indeed be possible, challenging long-held notions about the universe and the nature of existence itself. In this strange dance of particles and energy, the universe itself could be echoing a deeper truth, that the line between something and nothing is far blurrier than we ever thought. While quantum mechanics challenges our understanding of the incredibly small, other mysteries challenge our understanding of the immediate space around us. In October of 2017, an object unlike anything astronomers had ever seen entered our solar system. It did not originate from the asteroid belt or the distant Oort cloud that surrounds our sun. It came from deep interstellar space, moving at a speed too great to have been bound by the sun's gravity. The object was detected by the Pan-STARRS telescope in Hawaii and was eventually given the name Oumuamua. This is a Hawaiian term that roughly translates to scout or messenger from afar. The name was fitting, as its visit marked the first time in history that humans had definitively observed an interstellar object passing through our solar system. With it came a host of mysteries that remain unresolved to this day. The first anomaly was its shape. Most asteroids and comets that we are familiar with tend to be roughly spherical or potato-shaped lumps of rock and ice. But as astronomers analyzed the way Oumuamua reflected light while it tumbled through space, they realized it was incredibly elongated. It was estimated to be 10 times longer than it was wide, resembling a cigar or perhaps a flattened pancake. This extreme aspect ratio was unlike anything seen before in natural celestial bodies, and it immediately raised questions about how such an object could form and survive the stresses of interstellar travel. It didn't fit neatly into any of the categories astronomers use to classify objects in space. However, the shape was just the beginning of the puzzle. As Oumuamua passed through the inner solar system, astronomers noticed something else unusual about its behavior. Based on its appearance, it looked like an asteroid, a dry rock with no surface ice. Comets, which are made of ice and dust, tend to develop a glowing cloud called a coma and a long tail as they get close to the sun. This happens because the heat from the sun causes the frozen volatiles to sublime, turning directly into gas and blasting off the surface, creating a visible trail. Oumuamua showed no such behavior. Even as it passed relatively close to the sun, deep within the orbit of Mercury, there was no visible tail, no cloud of gas, and no sign of outgassing. To all visual inspections, it was a dead, dry rock. Yet, its motion told a different story. As it approached the sun, its trajectory followed the path governed by the sun's gravity, as expected. But after it passed the sun and began moving away, back toward interstellar space, something unexpected happened. The object accelerated. This acceleration was small, but it was statistically significant and enough to baffle astronomers. In celestial mechanics, objects move based on gravity. If an object speeds up or slows down in a way that gravity cannot explain, there must be another force acting upon it. For comets, this force is the rocket effect, caused by outgassing. As gas shoots out from the sun-warmed surface, it pushes the comet in the opposite direction. But Oumuamua had no visible gas. Without any evidence of outgassing or the typical signs of a comet, there was no clear physical explanation for why Oumuamua would speed up as it left the solar system. Gravity alone could not account for the change in the object's velocity. In the vacuum of space, trajectory is usually dictated by the gravitational pull of massive bodies, like the sun and planets. When an object deviates from this calculated path without a collision, there must be another force at work. For comets, this force is propulsion generated by the sublimation of ice, acting like a natural rocket engine. However, with Oumuamua, there were no visible means of propulsion, no jets of gas, no dust cloud, and no tail. This anomaly sparked intense debate within the scientific community, forcing researchers to propose creative and sometimes radical solutions to fit the data. One of the leading theories suggests that Oumuamua was not a fully formed planetary body, but rather a fragment of a planet that had been destroyed in another star system. In this violent scenario, a rocky world may have strayed too close to its host star, or a massive gas giant getting torn apart by immense tidal forces. The resulting debris would be flung outward, creating elongated shards of rock tumbling through the cosmos. Over millions or even billions of years, one of these shards traveled across the vast expanse of interstellar space, eventually entering our solar system by pure chance. This theory aligns well with the object's peculiar, elongated shape, similar to a splinter resulting from a break, but it struggles to explain the central mystery: the acceleration. A dry shard of rock should simply follow the path of gravity. It should not speed up as it moves away from the sun. To resolve this, another possibility was put forward: the hydrogen iceberg theory. This hypothesis suggests that Oumuamua was composed almost entirely of frozen hydrogen. Hydrogen is the most abundant element in the universe, and in the unimaginably cold depths of giant molecular clouds, the nurseries where stars are born, it can freeze into a solid state. If Oumuamua were a chunk of hydrogen ice, it would behave differently than the water ice comets we are used to. As it approached the sun, the hydrogen ice would sublime, turning from solid directly into gas. Crucially, hydrogen gas is transparent. It would not reflect sunlight or create a visible dust tail like standard comets. This invisible outgassing would provide the necessary thrust to accelerate the object, solving the movement mystery while explaining why our telescopes saw no tail. However, this theory also faces significant hurdles. Hydrogen ice is incredibly volatile and theoretical. We have never observed a macroscopic structure made of it in nature. Furthermore, some physicists argue that such an iceberg would have evaporated entirely during its long journey through interstellar space before it ever reached us. Yet, there is another, more speculative idea that has captured the imaginations of both some scientists and the general public. What if Oumuamua is not a natural object at all? Could it be an artificial artifact, perhaps a probe, a piece of defunct technology, or a listening device sent by another civilization? This idea, while far removed from mainstream consensus, was seriously proposed by respected researchers, including Avi Loeb, a theoretical physicist from Harvard University. Loeb and his colleagues suggested that the object's unusual acceleration could be the result of solar radiation pressure pushing against a very thin, lightweight structure, effectively a solar sail. If Oumuamua were artificial, it would explain the extreme shape, which could be designed to minimize friction or maximize surface area for propulsion, and the non-gravitational acceleration, which would be a feature of its design rather than a byproduct of evaporation. The idea that this visitor could be an alien probe is tantalizing, because it directly confronts one of humanity's oldest questions: are we alone? If a piece of technology from another star system can pass through our neighborhood, it implies a universe teeming with intelligent activity. However, the scientific community remains largely cautious. Extraordinary claims require extraordinary evidence. There were no radio signals detected coming from Oumuamua, no signs of heat waste that a machine might produce, and no maneuvers that clearly indicated intelligent control. The lack of direct technological signatures makes the alien hypothesis speculative at best. Whatever its true nature, whether a shard of a dead world, a ghost of hydrogen ice, or a silent messenger from a distant civilization, Oumuamua has reminded us of how little we know about the environment beyond the sun's influence. The object's visit was fleeting. It was visible to our best telescopes for only a few weeks before it faded into the dark, moving too fast to be chased. This brief window gave scientists only a fragmented data set. Despite the intense scrutiny, the fundamental questions remain unanswered. Where exactly did it come from? What forces shaped it? And why did it behave in a way that defied our standard models? Oumuamua has now returned to the interstellar void, taking its secrets with it. Speaking of the void, while Oumuamua traveled through the emptiness between stars, there are regions in the universe where emptiness is not just the space between objects, but the defining feature of the region itself. In the vast tapestry of the cosmos, filled with countless stars, glowing galaxies, and clouds of gas, there exists a region so barren that it stands out as a disturbing enigma. This region is known as the Boötes Void, located in the direction of the constellation Boötes. This is a nearly spherical region of space that stretches across an astonishing diameter of nearly 300 million light-years, with some estimates suggesting it influences an area up to 700 million light-years across. To put that scale into perspective, the distance from our Milky Way to our nearest major neighbor, the Andromeda Galaxy, is about 2.5 million light-years. The Boötes Void is vast enough to hold thousands of galaxies like ours, yet it does not. For a long time, its sheer emptiness baffled astronomers. We know that the universe is structured like a cosmic web. Dark matter forms long, invisible filaments that stretch across the universe, and galaxies tend to cluster along these filaments, or at the nodes where they intersect. Between these filaments are voids, giant bubbles of empty space. Voids are a normal part of the cosmic architecture. However, the Boötes Void is extraordinary in both its size and its extreme lack of galaxies. It is often referred to as the Great Nothing. When astronomers first mapped this region, they were struck by the statistics. In a volume of space this size, standard cosmological models predict there should be at least 10,000 galaxies. Instead, after decades of searching, we have found only about 60. To visualize this isolation, consider the words of astronomer Greg Aldering. If the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. This means human civilization would have developed with the belief that our galaxy was the only island in an infinite, dark ocean. We would have had no Andromeda, no distant clusters to observe, just an all-encompassing darkness beyond our own stars. This extreme emptiness has led some scientists to speculate whether the void is the result of unknown forces or perhaps even an artificial creation. Could there be a Type 3 civilization on the Kardashev scale that has harvested the energy of thousands of galaxies, effectively dimming them from our view? While this sounds like science fiction, the sheer anomaly of the void forces us to consider all possibilities. However, more grounded scientific theories focus on how the universe evolved. Most of space, at least as we perceive it, is made up of vast expanses of nothingness. But the Botez void is different. One leading theory suggests that it is a supervoid formed by the merger of several smaller voids over billions of years. As gravity pulled galaxies toward the denser filaments of the cosmic web, the spaces between them grew larger. The Botez void may be the result of a drainage effect, where the gravitational attraction of surrounding superclusters stripped this region of its matter, sweeping it clean like a cosmic broom. Alternatively, the void might reflect the conditions of the very early universe. After the Big Bang, matter was not perfectly evenly distributed. There were tiny fluctuations in density. Areas with slightly more matter had stronger gravity and pulled more material in, eventually forming galaxy clusters. Areas with slightly less matter lost what little they had to the denser regions, becoming increasingly empty. The Botez void could be a region that started with exceptionally low density, a primordial desert that has never been able to recover. When we look at this enormous cosmic hole, we confront a fundamental question. Does emptiness have a purpose, or is it simply the absence of structure? In the context of the cosmic web, voids are necessary. They are the negative space that defines the structure. Without the voids pushing matter away, a phenomenon known as dipole repulsion, the filaments and clusters where life can emerge might not have formed so densely. Yet, the Botez void is so extreme that it challenges our models of galaxy formation. Why is it so large? Why are the few galaxies inside it seemingly arranged in a tube shape running through the center? Could it be that in this region of space, the laws of gravity or dark energy operate slightly differently? For now, it remains a dark monument to the uneven nature of the universe. From regions where matter is perplexingly absent, we turn our attention to places where matter is dangerously close together. In the search for planets beyond our solar system, astronomers have uncovered a wide variety of strange and fascinating worlds. Among these discoveries, some exoplanets stand out because they seem to exist in direct defiance of the physical laws we understand. These are planets that survive in conditions so extreme, so seemingly impossible, that scientists are forced to question their models of planetary formation and longevity. These so-called impossible planets orbit their stars in configurations that contradict established theories. One of the most striking examples of this phenomenon is a planet known as WASP-18b, located roughly 330 light-years from Earth. WASP-18b is a gas giant, a massive world similar in size and composition to Jupiter, but with 10 times the mass. However, unlike Jupiter, which orbits the Sun at a comfortable, freezing distance, WASP-18b is locked in a lethal embrace with its parent star. The planet orbits so close to its star that by all conventional calculations, it should have been destroyed long ago. WASP-18b completes a full orbit its entire year in less than 24 hours. This means it is racing around its star at breakneck speeds. To maintain such a short orbital period, it must be located at an extraordinarily short distance from the star, just 1.9 million miles. To compare, Mercury, the innermost planet of our solar system, orbits at an average distance of 36 million miles. WASP-18b is practically skimming the surface of its sun. This extreme proximity creates a physical crisis involving tidal forces. Tidal forces are the gravitational interactions between two orbiting bodies. Just as the moon raises tides on Earth, WASP-18b raises massive tides on its star, and the star does the same to the planet. However, Because WASP 18b is so massive and so close, these forces are immense. According to the laws of orbital mechanics, this interaction creates drag. The star's rotation and the planet's orbit interact in a way that should rob the planet of its orbital energy. This process is known as orbital decay. Current theoretical models predict that a planet of this mass, at this distance, should be spiraling inward rapidly. The star's gravity should be dragging WASP 18b closer and closer, eventually tearing it apart or consuming it entirely. Based on the calculated age of the star, WASP 18b should have fallen into the star millions of years ago. It should not be there. And yet, there it is, defying expectations. The planet's continued existence implies that there is a flaw in our understanding of how tidal forces work in stars. Or perhaps there is a mechanism preserving the planet that we have not yet discovered. The friction from these tidal forces would also heat the interior of the planet to incredible temperatures, yet it remains stable. This survival in the face of certain destruction suggests that the interaction between massive planets and their stars is far more complex than the simple equations we currently use. The continued survival of WASP 18b defies the expected timelines of planetary destruction, leading some scientists to speculate that unknown factors must be at play. Perhaps the planet's internal structure is far denser than we assume, resisting the tidal deformation that would generate lethal heat. Or maybe its atmosphere possesses unique magnetic properties that shield it from the worst of the star's influence. But for now, WASP 18b remains a mystery, a survivor that refuses to adhere to our equations. It is not alone in its rebellion. There are other exoplanets that seem to actively mock our understanding of orbital mechanics. In our own solar system, order prevails. All the planets from Mercury out to Neptune orbit the Sun in the same direction that the Sun itself rotates. This is counterclockwise if viewed from above the Sun's North Pole. This uniformity is not a coincidence. It is a fossil record of our history. The solar system formed from a single, spinning disk of gas and dust. As the disk spun, everything within it moved in the same direction, preserving that initial angular momentum. This is a fundamental rule of planetary formation, or so we thought. In other star systems, we have found worlds that break this rule entirely. Planets like HATP7b and WASP 17b orbit their stars in the opposite direction of the star's rotation. This phenomenon is known as a retrograde orbit. Imagine a bustling highway where every car is moving east, and suddenly, a massive truck comes barreling down the lane heading west. That is the situation with these planets. They are effectively swimming upstream against the natural flow of their systems. The existence of retrograde planets contradicts the standard model of formation. A planet cannot form moving backwards within a forward-spinning disk. Therefore, something dramatic must have happened to alter its path after it formed. One possible explanation involves violent gravitational interactions, known as perturbations. In the chaotic early days of a star system, multiple massive planets might fight for space, a close encounter with another gas giant, or perhaps the gravitational influence of a distant companion star could act like a cosmic slingshot. This interaction could destabilize the planet, flipping its orbit wildly until it settled into a retrograde path. This process, sometimes referred to as the Kozai mechanism, suggests that planetary systems are not always the clockwork machines we imagine, but can be violent, chaotic arenas where worlds are tossed around like billiards. However, even this theory struggles to explain how a planet can undergo such a violent upheaval and then settle into a stable, albeit backward, orbit without being ejected into deep space. Then there are planets whose defiance is not just in their direction, but in their sheer proximity to danger. We call them hot Jupiters. These are gas giants that orbit their stars at distances so close they are practically touching the solar surface. The heat and radiation in these zones are intense enough to strip away atmospheres and boil rock, yet these planets persist. Consider Kepler 78b. This is not a gas giant, but a rocky world about the size of Earth. However, unlike our temperate home, Kepler 78b is a hellscape. It orbits its star so closely that it completes an entire year, one full revolution in just 8.5 hours. Imagine celebrating New Year's 3 times a day. At this distance, the surface temperature is estimated to be over 2,000 degrees Celsius. The entire surface of the planet is likely a continuous ocean of molten lava. According to our understanding of orbital dynamics, Kepler 78b should not exist. A planet cannot form that close to a star. The star's gravity would have prevented the dust and rock from coalescing into a planet. This means Kepler 78b must have formed farther away and moved inward. But even then, existing models predict that once a planet gets this close, the tidal forces should cause its orbit to decay rapidly. It should have spiraled into the star and been vaporized eons ago. Yet, the data confirms it is there. Its existence forces scientists to rethink the lifespan of planets in extreme environments. Are we underestimating the resilience of rocky worlds? Or is there a stabilizing force we have yet to account for? These impossible planets, WASP-18b, HATP-7b, and Kepler 78b, suggest that the universe is far more diverse and unpredictable than the sample size of our own solar system led us to believe. Our system, with its neat, circular orbits and orderly arrangement, might be the exception rather than the rule. The discovery of these anomalies has sparked new avenues of research. Scientists are now exploring the concept of planetary migration in greater depth. It is possible that these planets formed in the cold, safe outer reaches of their systems and were dragged inward by friction with the remaining gas disk or pulled by the gravity of other planets. This migration could explain how a gas giant like WASP-18b ends up in a scorching orbit. But migration takes time, and stopping the planet right at the edge of destruction without pushing it over requires a delicate balance of forces that we do not fully understand. Other researchers are looking inward, at the planets themselves. Perhaps the internal structure of these worlds is different. A stronger magnetic field could protect the atmosphere from being stripped away by stellar winds. A denser core might resist tidal disruption. We are still in the early stages of characterizing these distant worlds. For now, they stand as reminders that our knowledge is provisional. We have modeled the universe based on our own backyard, but the neighborhood is full of surprises. From the chaotic orbits of individual planets, we zoom out to the largest scales imaginable, where the anomalies are not about what is there, but what is missing. We have spoken of the Botti's void, but there is another region of emptiness that is even more perplexing, both for its size and its chilling temperature. This is the Eridanus supervoid. In the standard model of cosmology, the universe is uniform on large scales. If you take a big enough box of the universe, it should look roughly the same as any other box of the same size. Matter, galaxies, and energy should be distributed fairly evenly, but the Eridanus supervoid breaks this rule. Located in the direction of the constellation Eridanus, this is a region of space that appears to be almost completely devoid of galaxies, stars, and gas. What makes the Eridanus supervoid truly staggering is its size. It spans nearly 1 billion light-years across. It is a hole in the universe so vast that it defies our theories of how cosmic structures grow. In the time since the Big Bang, about 13.8 billion years, there simply hasn't been enough time for gravity to clear out a space this large. Standard voids, like bubbles in a sponge, are expected, but a void of this magnitude is like finding a cavern in the sponge larger than the sponge itself. The mystery of this supervoid is deepened by how it was discovered. It wasn't found by counting galaxies, but by looking at the oldest light in the universe, the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a radiation that fills the entire sky. It is almost perfectly uniform, with a temperature of about 2.7 Kelvin. However, there are tiny fluctuations, hotter spots and colder spots, that represent the seeds of future galaxies. In 2004, astronomers analyzing this map noticed a massive, anomalous, cold spot in the southern hemisphere. This spot was significantly larger and colder than standard statistical fluctuations allowed. For years, scientists debated its cause. Was it an error in the instrument? A statistical fluke? Eventually, studies aligned this cold spot with the location of the Eridanus supervoid. The connection makes sense through a phenomenon known as the integrated Sachs-Wolf effect. As photons of light from the CMB travel through the universe, they gain energy, falling into the gravity wells of galaxy clusters, and lose energy climbing out. In a normal universe, these cancel out, but when light travels through a massive void, it enters a hill rather than a well. As the universe expands while the light is crossing this vast billion light-year emptiness, the light loses energy, becoming colder. The Eridanus supervoid is so huge that it literally sucked the energy out of the ancient light passing through it, leaving a cold shadow on the sky. But here is the problem. Even with this effect, the void is too big and too empty to be explained by standard gravity alone. This has led to one of the most provocative theories in modern cosmology. Some theoretical physicists, looking for an explanation that fits the scale of the anomaly, have proposed that the Eridanus supervoid might be a scar from a collision with another universe. This idea stems from multiverse theory, which suggests our universe is just one bubble in an infinite, frothy sea of other universes. According to this hypothesis, early in our universe's history, another bubble universe might have bumped into ours. The bruise from this cosmic impact would push matter away, creating a vast region of emptiness and leaving a distinct cold signature on the radiation background. If this theory holds true, the Eridanus supervoid is not just an empty space. It is the first physical evidence that we are part of a much larger multiverse. While the parallel universe theory is highly speculative and lacks direct proof, the alternative explanations are equally challenging. Some suggest that dark energy, the mysterious force driving the universe's expansion, might be acting strangely in this region, pushing matter apart faster than elsewhere. Others wonder if it is a statistical anomaly, a random fluctuation that just happens to look significant. But as data improves, the void remains cold and vast, challenging our assumption that the universe is the same everywhere, whether it is a window into the multiverse or a puzzle of dark energy. The Eridanus supervoid stands as a testament to the unknown. It suggests that the cosmos is not just a uniform spread of matter, but a landscape with features so colossal they dwarf our imagination. From the mysteries of the dark and empty, we turn to a mystery of light. In the constellation Cygnus, over 1,400 light-years away, there is a star that has triggered one of the biggest detective stories in 21st century astronomy. Its official designation is KIC 8462852, but it is better known as Tabby's star, named after the astronomer Tabitha Boyajian, who led the paper announcing its discovery. To the naked eye, or even a standard telescope, Tabby's star looks like an ordinary F-type main sequence star, slightly hotter and bigger than our sun, but otherwise unremarkable. However, in the data collected by the Kepler Space Telescope, which monitors stars for the tiny dips in brightness caused by transiting planets, Tabby's star did something extraordinary. Normal planets block a tiny fraction of a star's light, usually less than 1%, and they do so in a regular, repeating pattern. Jupiter, for instance, would block about 1% of the sun's light, but Tabby's star showed massive, irregular dips in brightness. At one point, the star's light plunged by 15%. Later, it dropped by a staggering 22%. These dips lasted for days at varying intervals, showing no clear orbital pattern. Whatever was blocking the light was not a planet. It was huge, irregular, and constantly changing. The behavior was so bizarre that when the data was first analyzed, astronomers assumed the telescope was malfunctioning, but the checks confirmed the signal was real. Something massive was orbiting Tabby's star, blocking vast amounts of light in a chaotic way. This kicked off a frenzy of hypothesis generation. Was it a swarm of comets, a planetary collision, or something artificial? In 2015, the mystery of Tabby's star deepened significantly. Researchers analyzing data from the Kepler Space Telescope, which had been staring at this patch of sky for 4 years, noticed something that defied all conventional explanations. Typically, when a planet passes in front of a star, the dimming is consistent and rhythmic, like a clock ticking. The light drops by a small fraction, usually less than 1%, stays down for a few hours, and then returns to normal. This happens at regular intervals, marking the planet's orbit. But the light curve of Tabby's star was nothing like a ticking clock. It was a chaotic drumbeat. The dips in brightness were erratic, irregular, and terrifyingly deep. At one point, the star's light plummeted by 15%. In another instance, it dimmed by a massive 22%. To put this in perspective, even a planet the size of Jupiter, the largest in our solar system, would only block about 1% of the sun's light. For a star to dim by 22%, something colossal must be blocking it, something roughly half the width of the star itself. And unlike a spherical planet, this object seemed to have no defined shape, and the dimming events followed no predictable schedule. This peculiar behavior led to a flurry of speculation. Natural explanations struggled to fit the data. Dust clouds are usually warm and emit infrared radiation, but Tabby's star showed no excess heat. A collision between planets would create a specific type of debris that wasn't seen. Faced with the impossible, astronomers had to consider the improbable. The most sensational of these theories suggested the possibility of an alien megastructure. This idea is rooted in the work of physicist Freeman Dyson, who theorized that an advanced civilization, one that has outgrown the energy resources of its home planet, might construct a massive shell or swarm of solar collectors around its star to harvest all of its energy. This is known as a Dyson sphere or Dyson swarm. If such a structure were incomplete or composed of giant, independent panels orbiting the star, it could theoretically block massive amounts of light in irregular patterns, exactly matching what was observed at Tabby's star. The notion captured the public imagination instantly. It evoked images of vast, spacefaring civilizations, engineering on a scale that makes our greatest achievements look like sandcastles. If Tabby's star was indeed being dimmed by such a megastructure, it would be the first tangible evidence of intelligent life beyond Earth. it would change human history overnight. However, in science, the most exciting answer is rarely the correct one without extraordinary proof. The alien megastructure hypothesis, while captivating, remains highly speculative. Following the initial excitement, astronomers turned the world's most powerful radio telescopes, including the Green Bank telescope, toward the star to listen for signals. They looked for narrowband radio transmissions, or laser pulses, signs of communication or propulsion. They heard nothing. The star was silent. Furthermore, later analysis showed that different colors of light were being blocked at different intensities. A solid object, like a solar panel, would block all light equally, making the star dimmer but not changing its color. Dust, however, blocks blue light more than red light. The data from Tabby's star showed this chromaticity, suggesting that the blocking material was likely somewhat transparent, more like a cloud of fine particles than a solid metal structure. While the alien theory faded from the mainstream, it left the door open for other, equally complex natural explanations. One of the leading theories is that the star is being swarmed by a family of giant comets. In this scenario, a massive comet, perhaps the size of a dwarf planet, could have been shattered by the star's gravity, or a collision. This would create a chaotic train of debris, huge chunks of ice and rock surrounded by massive clouds of gas and dust. As these fragments travel on highly elliptical, eccentric orbits, they would pass in front of the star at odd intervals. The tails of these comets could be millions of miles long, creating the extended, irregular dimming events. Yet, even this theory has holes. To block 22% of the light, the swarm would need to be unimaginably dense, and we haven't seen the specific chemical signatures of cometary gas that we would expect. Another possibility involves the destruction of a moon. Some researchers, termed plunettes, suggest that a large exomoon could have been stripped from its planet and slowly disintegrated by the star's heat, shedding vast amounts of dust into a ring. As this uneven ring of dust drifts in and out of our line of sight, it creates the strange flickering. Dust is a prime suspect because, as mentioned, it scatters blue light differently than red, fitting the later observations. But this dust would need to be incredibly fine and transient to avoid creating the infrared heat signature that is seemingly missing. There are also more exotic possibilities that look inward rather than outward. Could the star itself be the culprit? Standard stellar physics says that F-type stars should be stable. They don't just dim by 20% on a whim. However, we are still learning. Some researchers propose that Tabby's star might be undergoing a rare internal phase transition, a magnetic avalanche, or a shift in its convection currents that cools the surface temporarily. Or perhaps it recently swallowed a planet, and we are seeing the star burp as it digests the extra mass, resulting in temporary dimming as the equilibrium is restored. This would suggest that stars are far more dynamic and volatile than our current textbooks admit. Despite years of intense study and a successful Kickstarter campaign that raised money to keep telescopes pointed at the star, there is no single smoking gun explanation. The mystery remains, and in many ways, that is better than a quick answer. The saga of Tabby's star is a triumph of modern astronomy, not because we solved it, but because of how we found it. It brings us to a crucial point about discovery, the role of the human eye. Tabby's star was not flagged by a computer algorithm. Algorithms are designed to find patterns. They are taught to recognize repeating signals. Standard transits, they often miss the weird stuff. Tabby's star was identified by citizen scientists, ordinary people participating in the Planet Hunters project. These volunteers stared at light curves on their home computers, and flagged the data as bizarre. They saw what the machines missed. It serves as a powerful reminder that in an age of artificial intelligence and automated surveys, human curiosity and pattern recognition are still indispensable tools. As the investigation continues, it raises deeper philosophical questions. What do we do when faced with a mystery that refuses to be solved? How do we balance the skepticism required by science with the excitement of potential breakthroughs like alien life? In a universe as vast as ours, Tabby's star is likely just the first of many such anomalies waiting in the dark. Whether it is a swarm of comets, a dying moon, or something we haven't even imagined yet, it stands as a beacon of our ignorance, inviting us to keep looking. From the chaotic, flickering shadows of Tabby's star, we move to a mystery defined by the opposite: perfect, eerie order. In the distant reaches of space, most nebulae, the clouds of gas and dust where stars are born and die, are chaotic. Think of the Orion Nebula or the Eagle Nebula. They are swirling, organic shapes, full of lumps, filaments, and amorphous clouds. They look like paintings made by spilling ink on a canvas, beautiful but random. But nestled within the Milky Way, about 2,300 light-years from Earth, towards the constellation Monoceros, there is an object that defies this rule. It is known as the Red Rectangle Nebula. It stands out immediately, not just because of its vivid color, but because of its geometry. In a universe governed by fluid dynamics and gravity, nature rarely draws straight lines. Yet, the red rectangle presents a shape of unnerving precision. Seen from Earth, it looks like a glowing red X with long, parallel spikes extending outward, framing a series of rungs like a ladder. These lines form what appears to be a perfect rectangle, a sharp, symmetrical box floating in the dark. It looks less like a cloud and more like a structure, a piece of cosmic architecture carved with intention. At the heart of this geometric wonder lies a binary star system. Two stars are locked in a tight orbit around each other, hidden deep within the dense dust at the center. It is from this central engine that the nebula's strange shape originates. But how do two round stars create a square nebula? The answer lies in a trick of perspective and complex fluid dynamics. Scientists believe that the rectangle is actually an optical illusion created by two cone-shaped flows of gas interacting. Imagine two ice cream cones joined at their tips. The stars at the center are ejecting gas in opposite directions, but not randomly. Thick disks of dust around the stars act like nozzles, funneling the gas into these precise cone-shaped jets. Now, imagine looking at those cones exactly from the side. The edges of the cones form an X shape. The rungs of the ladder are actually shock waves, ripples in the gas, caused by the stars' periodic outbursts as they dance around each other. Because we are viewing this three-dimensional hourglass shape from a specific angle, it appears to us as a flat, two-dimensional rectangle. If we were to view it from the top down, it might look like a target or a spiral, but from our vantage point, it becomes a study in impossible geometry. The precision of these lines is startling. The outflows have remained stable for thousands of years, creating layers of dust that are spaced with mathematical regularity. This level of symmetry suggests a highly stable environment where the stellar winds are sculpted by strong magnetic fields or the precise gravitational interaction of the binary pair. It challenges our understanding of stellar death, showing that the process of a star shedding its outer layers can be incredibly orderly, almost like a machine. Adding to the mystery is the nebula's distinct color. The red rectangle glows with an intense, rich red hue that is not common in reflection nebulae, which usually appear blue. This red glow is a chemical mystery. Spectroscopic analysis reveals that the nebula is rich in carbon-based molecules known as polycyclic aromatic hydrocarbons, or PAHs. PAHs are complex organic compounds. On Earth, we find them in the soot from a candle, the exhaust of a car, or the char on a grilled steak. They are the byproducts of combustion. Finding them in such vast quantities in space, glowing under the ultraviolet radiation of the central stars, tells us that this nebula is a massive chemical factory. It is synthesizing the building blocks of organic chemistry on a cosmic scale. The specific type of red light emitted here, known as extended red emission, is a phenomenon that is still not fully understood. It suggests that the dust grains in the red rectangle have unique properties, perhaps interacting with the strong ultraviolet light in ways we cannot yet reproduce in a lab. The Red Rectangle Nebula, with its straight lines and sharp angles, serves as a counterpoint to the chaos of Tabby's star. One is a mystery of unpredictable disorder. The other is a mystery of impossible order. Both remind us that the forces sculpting the universe are capable of creating forms that challenge our imagination. Some researchers have even speculated that magnetic fields play a much larger role here than gravity, acting as invisible containment walls that force the gas into these rigid shapes. Others wonder if the interaction between the two stars is creating a warp in the disk, modifying the outflow in periodic ways. These ideas remain unproven, but they reflect the sense of wonder that the red rectangle inspires. It is a reminder that in space, natural does not always mean random. Sometimes, physics can draw with the precision of an architect. To understand the red rectangle, we must look at the engine driving it. The central point of light is not a single star, but a binary system, two stars locked in a gravitational dance. The primary star is an aging red giant, a star that has exhausted its hydrogen fuel and swollen to a massive size. As it nears the end of its life, it is pulsating, shedding its outer layers of gas and dust into space. This is a standard phase in stellar evolution, but usually this process is messy and spherical, like a bubble expanding in all directions. In the red rectangle, however, there is a companion star. This second star, likely a smaller, denser, white dwarf, plays a crucial role. As the red giant expels material, the gravity of the companion star captures and redirects it. The interaction creates a thick, dense ring of gas and dust that encircles both stars. Astronomers call this a circumbinary disk. Think of this disk as a constricting nozzle on a hose, or the potter's hands shaping clay on a wheel. The disk is so dense that the gas escaping from the red giant cannot expand outward in all directions. Instead, it is forced to shoot out from the poles of the system, perpendicular to the disk. These focused jets of gas create two hollow cones extending into space. Over thousands of years, as the stars orbit each other, the periodic pulses of gas create the rungs or shock waves we see. What appears to us as a flat, sharp-edged rectangle is actually a three-dimensional X-shaped structure, viewed from the side, illuminated by the light of the stars reflecting off the dust particles. Despite having a working theory, the red rectangle remains a provocation to astronomers. The geometry is simply too precise. Cosmic clouds are typically subject to a barrage of chaotic forces, stellar winds, radiation pressure, and interstellar turbulence that tend to churn gas into irregular, fluffy shapes. The fact that the red rectangle has maintained such razor-sharp symmetry over thousands of years suggests a level of stability that is difficult to explain. It implies that there may be additional sculpting forces at play, perhaps strong magnetic fields that act like invisible walls, confining the gas to its rigid path. In a broader sense, this nebula challenges our perception of order and chaos. We often view the universe as a place defined by randomness and violent unpredictability. Yet, structures like the red rectangle show that under the right conditions, perfect symmetry can emerge from the turbulence. It stands as a reminder that the laws of physics are the ultimate architects, capable of drawing straight lines even in the smoke of a dying star. For astronomers, studying this object is not just about understanding one nebula, it is about unlocking the fluid dynamics of the cosmos. Every sharp angle and straight line offers data on how binary stars interact and how matter behaves in the extreme vacuum of space. From the tightly bound partnership of the red rectangle, we turn our attention to objects defined by their total lack of connection. In the traditional image of the cosmos, planets are the children of stars, bound to them by gravity, basking in their warmth, and circling them in predictable years. This is the model of our solar system and the thousands of exoplanet systems we have discovered. But not all planets fit this mold. Scattered throughout the darkness, far from the light of any sun, are the rogue planets, also known as orphan planets or free-floating planets. These are worlds that drift alone through the interstellar void. They possess no sunrise, no sunset, and no years to measure time by. They travel in eternal night, locked in a cold isolation that is difficult for us to comprehend. For a long time, these planets were purely theoretical ghost stories of astronomy. But in recent years, we have confirmed that they are real, and they may be far more common than anyone dared to imagine. The existence of rogue planets forces us to rewrite the history of planetary formation. How does a planet end up alone? The leading theory suggests that most of them were born inside normal solar systems. In the chaotic early days of a star system's formation, planets do not stay in neat lanes. Gas giants migrate inward and outward, their gravity pulling and pushing at their neighbors. In this cosmic game of billiards, smaller planets can be caught in the gravitational crossfire. If a planet passes too close to a massive gas giant like Jupiter, the gravitational sling can accelerate it to escape velocity, ejecting it from the solar system entirely. Cast out by its own siblings, the planet flies into the dark, untethered from the star that made it. There is, however, a second possibility. Some rogue planets may never have had a star to begin with. In the same vast clouds of gas and dust where stars are born, smaller knots of matter can collapse under their own gravity. If the clump of gas is too small, lacking the mass to ignite nuclear fusion, it becomes a sub-brown dwarf or a gas giant that simply forms in isolation. These are worlds that were born alone. Whatever their origin, the environment on a rogue planet is vastly different from what we know. Without a star to provide external energy, these worlds would appear to be frozen wastelands. The surface temperatures would approach absolute zero, freezing any atmosphere into solid ice on the surface. At first glance, they seem like the least likely places in the universe to harbor life. But science teaches us to look deeper. Beneath the frozen crust of a rogue planet, conditions might be surprisingly active. A planet does not need a sun to be warm. It carries its own heat source deep within its core. This comes from the decay of radioactive elements like uranium and thorium, a slow-burning nuclear battery left over from the planet's formation. For a rocky planet with a thick, insulating layer of ice, This internal heat could be enough to maintain pockets of liquid water deep underground. Furthermore, if the rogue planet traveled with a moon, which is entirely possible, it could benefit from tidal heating. As the moon orbits, its gravity stretches and squeezes the planet's core, generating friction and heat from the inside out. We see this in our own solar system on Jupiter's moon Europa, which has a subsurface ocean kept liquid by tidal forces. On a rogue planet, this same mechanism could sustain a global ocean beneath kilometers of shielding ice. This realization has expanded the boundaries of astrobiology. We used to think the habitable zone was a narrow ring around a star where water could exist. Rogue planets suggest that habitable environments could exist in the dead of interstellar space, powered not by light, but by geology. If life can thrive around volcanic vents at the bottom of Earth's oceans, far from the sun, could microbial life also exist in the dark, warm oceans of a wandering planet? It is a speculative but scientifically grounded possibility. Detecting these lonely worlds is one of the hardest challenges in astronomy. They emit almost no light of their own, and they reflect nothing. They are essentially invisible. To find them, astronomers rely on a technique called gravitational microlensing. This method uses the laws of general relativity. When a rogue planet passes exactly in front of a distant background star, the planet's gravity acts like a lens. It bends and focuses the light of the background star, causing the star to briefly appear brighter. It is a fleeting event, a tiny spike in brightness that happens once and never again. By monitoring millions of stars and waiting for these random alignments, scientists have begun to build a census of the dark. One of the most famous candidates is an object with the designation CFB-DSIR 2149-0403, located about 100 light-years away. It appears to be a gas giant with 4 to 7 times the mass of Jupiter, drifting without a star. Its discovery proved that such objects are within our observational reach. The implications of these discoveries are staggering. Some statistical models suggest that rogue planets might outnumber the stars in our Milky Way galaxy. Think about that for a moment. For every star you see in the night sky, there could be one, or perhaps many, invisible planets moving through the spaces in between. They could range from small, rocky, Earth-sized worlds to massive Jupiters, creating a hidden population of the galaxy that rivals the visible one. In the quiet, predictable movements of stars within a galaxy, there are certain patterns astronomers have come to expect. Stars generally follow stable, elliptical orbits around the galactic center, moving at speeds that, while fast to us, are consistent with the galaxy's overall rotation and gravitational balance. However, scattered among the predictable orbits of the galaxy, there are outliers, rebels, that refuse to conform to the majestic rotation of the spiral arms. These are the rogue stars. But unlike the drifting planets that wander in silence, these objects are defined by their violence and speed. We call them hypervelocity stars. While a typical star in the Milky Way orbits the galactic center at a respectable pace of a few hundred kilometers per second, hypervelocity stars are moving at speeds that defy common sense. They can travel at over 1,000 kilometers per second, that is more than 2 million miles per hour. To put that in perspective, at this speed, you could travel from the Earth to the Moon in under 6 minutes. This velocity is significant not just because it is fast, but because it exceeds the galactic escape velocity. These stars are moving so quickly that the gravity of the entire galaxy is not strong enough to hold them back. They are breaking the chains of gravity and racing into the vast, terrifying emptiness of intergalactic space. The discovery of these stars has shed new light on the extreme forces that operate in the most chaotic environments of the universe. But what kind of force could possibly kick a star, an object with a mass millions of times greater than the Earth, hard enough to eject it from a galaxy? The answer leads us to the monsters lurking in the dark. Supermassive black holes. One of the most widely accepted explanations, known as the Hill's mechanism, suggests that these stars are the survivors of a cosmic tragedy. Most stars in the universe are not alone. They exist in binary systems where two stars orbit each other. If such a pair wanders too close to the supermassive black hole at the center of our galaxy known as Sagittarius A, times the gravitational tidal forces become overwhelming. The black hole's gravity can pull the binary pair apart. In a gravitational exchange of energy, one star is captured and pulled into a doomed orbit around the black hole, eventually to be consumed. But the other star is whipped away. It steals energy from its lost companion and is flung outward at incredible speed. It is a cosmic slingshot effect, launching the survivor on a one-way trip out of the galaxy. One of the first confirmed examples of this phenomenon, a star named HVS-1, was discovered in 2005 by astronomers using the MMT Observatory in Arizona. It was clocked moving at over 700 kilometers per second, more than twice the speed needed to escape the galaxy's pull. Tracing its path backward, astronomers found that it originated directly from the galactic center, confirming its violent history with Sagittarius A*. Since then, we have identified dozens of these exiles, each carrying the kinetic scars of a close encounter with the most powerful object in our galaxy. The journey of a hypervelocity star is a lonely one. Once ejected, it leaves behind the star-forming regions and the spiral arms. It crosses the galactic halo, the spherical cloud of old stars and dark matter surrounding the galaxy, and eventually enters the void. Intergalactic space is the truest definition of emptiness. The distance between galaxies is measured in millions of light years. Once a hypervelocity star enters this realm, it will likely never encounter another object again. It will burn through its fuel in absolute isolation, drifting for billions of years in the dark gap between the islands of the universe. However, these stars are not just tragic figures, they are useful tools. Because they travel from the center of the galaxy to its furthest edges, they act as probes. As they move, their trajectory is affected by the gravity of everything they pass. By studying their paths, astronomers can map the distribution of dark matter in the galactic halo, the invisible scaffolding that holds our galaxy together. They are test particles moving through the gravitational field, revealing the shape of the galaxy in ways we could not see otherwise. There is another way these stars can be born, involving collisions on a much grander scale. When two galaxies interact or merge, the chaotic fluctuation of gravitational fields can act like a catapult, flinging stars out of the system entirely. In these complex interactions, a star might be accelerated to hypervelocity speeds, either by the collision itself or by the gravitational influence of a supermassive black hole from the merging galaxy. This reminds us that galaxies are not static, isolated paintings, but dynamic, evolving environments where stars can be born, destroyed, or exiled into the depths of space. From the chaotic, high-speed ejection of individual stars, we turn our attention to a structure that is baffling for the opposite reason. It's uncanny, frozen perfection. Galaxies come in many shapes, spirals like our Milky Way, blobs like ellipticals, and messy irregulars. But in 1950, an astronomer named Arthur Hogue discovered an object that defied all these categories. Located about 600 million light years away in the constellation Serpens, It is now known simply as Hoag's object. At first glance, Hoag's object looks artificial. It is a nearly perfect, detached ring of blue stars circling a bright, golden core, with nothing but darkness in between. It looks less like a galaxy and more like a diagram of a planetary system or a cosmic eye staring back at us. This is a rare type of galaxy known as a ring galaxy. The structure is striking in its contrast. The outer ring is dominated by bright blue stars. In astronomy, blue signifies youth. These are hot, massive stars that burn through their fuel quickly, meaning this ring formed relatively recently in cosmic terms. Inside this ring sits a sphere of yellow and red stars. Red signifies age. These are older, cooler stars that have been burning for billions of years. What makes Hoag's object truly peculiar is the gap between the blue ring and the red core. There appears to be almost nothing, a vast, transparent region where few stars exist. Through this gap, if you look closely at high-resolution images, you can actually see another, much more distant ring galaxy in the background, a Hoag's object within Hoag's object. But the main mystery is its geometry. Most ring galaxies we observe are messy. They are usually the result of a violent collision where a smaller galaxy punches through the center of a larger spiral galaxy like a bullet. This impact creates a density wave, a ripple of gravity that spreads outward, compressing gas and triggering star formation in a ring, much like the ripples in a pond after you throw a stone. This is the standard collisional ring theory. However, if Hoag's object were formed by such a collision, we should see the bullet. The intruder galaxy that punched through should still be nearby, likely distorted by the impact. Astronomers have searched the area around Hoag's object extensively, but the culprit is missing. The galaxy sits in relative isolation. There are no nearby companions large enough to have caused such a perfect structure, and there are no telltale trails of gas or streams of stars that usually linger after a crash. The ring is smooth, symmetrical, and centered perfectly on the core. It lacks the chaos of a recent collision. This has led scientists to look for alternative explanations. One theory, known as the bar instability hypothesis, suggests that this was a slow, internal process. Perhaps billions of years ago, Hoag's object was a barred spiral galaxy, similar to the Milky Way. Over time, the central bar structure became unstable and dissolved. The rotation of the galaxy then caused the gas to drift outward, accumulating in a resonance ring where it eventually collapsed to form the circle of blue stars we see today. This quiet formation theory would explain the lack of a collider and the perfect symmetry. It suggests that the galaxy transformed itself from the inside out, rather than being shaped by an external force. Yet, creating such a clean separation between the core and the ring without a violent event is difficult to simulate in computer models. Hoag's object remains a unique laboratory for studying galaxy evolution. It challenges the standard models that rely on mergers and collisions to explain odd shapes. Whether it is the fossil of a vanished intruder or the result of a slow, graceful internal drift, it stands as one of the most aesthetically perfect mysteries in the sky. Its existence forces us to ask, how can nature, which usually favors entropy and disorder, produce something so geometric and precise without leaving a single scar of the process? One leading theory posits that Hoag's object could be the result of a rare gravitational phenomenon known as a resonant ring. In this scenario, the galaxy's history involves a delicate interaction rather than a violent collision. Billions of years ago, a smaller galaxy or a significant concentration of dark matter might have passed near the core of what would become Hoag's object. Instead of crashing through, this visitor could have skirted the edges, creating a gravitational disturbance, a rhythmic tug. This subtle interaction would have set up a gravitational resonance, similar to how pushing a swing at the right moment increases its height. These resonances create stable zones, or lanes, in the galaxy's disk, where gas and dust naturally accumulate. Over time, the gas in the outer reaches was shepherded into a circular orbit where it grew dense enough to collapse and ignite into stars. This mechanism would explain the nearly perfect symmetry of the galaxy, as the gravitational forces involved would have distributed the material in a balanced, circular fashion, essentially locking the stars into a stable, geometric trap. However, no direct evidence of such a passing object has been found, leaving this theory as a plausible but unproven mathematical solution. Another compelling idea suggests that Hoag's object formed through an internal blowout process. In this model, the galaxy's core formed first, consuming most of the available gas in the center to create the dense ball of yellow and red stars we see today. These stars then aged, their fierce stellar winds pushing the remaining loose gas outward. Imagine a shockwave or a snowplow of pressure moving from the center toward the edge of the galaxy. As this wave traveled outward, it compressed the interstellar medium. Once the gas reached a critical density at the galaxy's periphery, it triggered a massive burst of star formation, lighting up the ring with young, hot, blue stars. This would explain the distinct separation. A fossilized core, surrounded by a nursery of new stars, separated by a gap that had been swept clean of material. Yet, simulations of this process rarely produce rings as perfectly round and detached as Hoag's object, keeping the mystery alive. Adding to the intrigue is the fact that while Hoag's object is rare, it is not entirely unique. We have observed other ring galaxies, such as the Cartwheel Galaxy, but they almost always tell a violent story. They show signs of disruption, warped edges, chaotic debris trails, or the visible remnants of the collider galaxy nearby. Hoag's object stands apart because it appears remarkably undisturbed. It looks as though it has maintained its serene form for billions of years, isolated in a quiet corner of the universe. This raises questions about stability. How long can a structure like this survive? In the dynamic environment of the cosmos, rings are often transient features that eventually disperse or collapse back into the center. The persistence of Hoag's object suggests that whatever mechanism created it established an equilibrium that is exceptionally robust. In the decades since its discovery, our view of this galaxy has sharpened. Observations with the Hubble Space Telescope have peeled back the layers of blurriness, revealing the intricate knots of star clusters within the blue ring. But these images also revealed a surprising, almost poetic feature hidden in the background. Visible through the transparent gap between the golden core and the blue ring, at the roughly 1 o'clock position, sits another ring galaxy. This is a background object, located far behind Hoag's object, yet aligned perfectly with the gap. It is a Hoag's object within Hoag's object. The statistical odds of two such rare, perfect ring galaxies aligning in our line of sight are infinitesimal. This discovery acts like a cosmic hall of mirrors, deepening the sense of mystery. It reminds us that we are looking through a universe with depth, where anomalies can stack upon anomalies. Despite these advances, no consensus has been reached. Hoag's object remains a beautiful anomaly, a challenge to our textbooks on galactic evolution. It invites us to consider that nature may have pathways to order that we have not yet modeled. From the silent, cold perfection of a distant ring, we turn our gaze inward to the chaotic, and energetic heart of our own galaxy. Deep within the center of the Milky Way, approximately 26,000 light-years from Earth, lies a region shrouded in thick clouds of dust and gas. Optical telescopes cannot penetrate this veil, but when astronomers look at this region with instruments sensitive to high-energy radiation, they see something glowing with intense brightness. It is a source of gamma rays, the most energetic form of light in the universe. This glow is not uniform. It is a specific signal, a spike in energy that corresponds to a very particular physical process, the annihilation of antimatter. Antimatter sounds like the stuff of science fiction, but it is a fundamental part of particle physics. For every particle of ordinary matter, there is an antimatter counterpart with the same mass, but an opposite electric charge. The electron, which carries a negative charge, has a twin called the positron, which carries a positive charge. When a particle of matter meets its antimatter twin, they do not bounce off each other or bond. They destroy each other. They annihilate instantly, converting their entire mass into pure energy in accordance with Einstein's equation, E equals mc squared. This reaction releases gamma rays at a very specific energy level, 511 kiloelectron volts. When astronomers point their detectors at the galactic center, they see a massive, bright signal at exactly 511 kiloelectron volts. This tells us, without a doubt, that a fountain of antimatter is active in the core of our galaxy. The scale of this phenomenon is staggering. To produce the amount of gamma radiation we observe, roughly 10 to the power of 43 positrons, must be annihilating every second. That is an unimaginable amount of antimatter being destroyed continuously. The question that haunts astrophysicists is, where is it all coming from? Under current cosmological theories, the universe today is dominated by matter. Antimatter is rare, usually produced only in high-energy nuclear reactions. There simply shouldn't be enough of it floating around the galactic center to create such a bright signal. The persistence of this antimatter fountain implies that something in the core is manufacturing positrons on an industrial scale. One possible explanation involves the remnants of dead stars. The galactic center is a graveyard of stellar history, densely packed with neutron stars and black holes. Some of these neutron stars are pulsars, highly magnetized, rapidly spinning cores that act like cosmic dynamos. The magnetic fields around a pulsar are trillions of times stronger than Earth's. In these extreme environments, the magnetic force can be so intense that it rips particles out of the vacuum itself, creating pairs of electrons and positrons. These particles are then accelerated to near the speed of light as they stream away from the pulsar and collide with the surrounding gas of the interstellar medium. The positrons annihilate, releasing the gamma rays we see. Given the high density of stars in the galactic center, a population of thousands of unresolved pulsars could theoretically account for the signal. Another prime suspect is the monster at the very center, Sagittarius A*, the supermassive black hole. Black holes are known to be messy eaters. As gas and dust spiral inward toward the event horizon, they form an accretion disk that heats up to millions of degrees. The chaotic magnetic fields in this disk can launch jets of plasma and high-energy particles outward. It is possible that the extreme conditions near the event horizon are acting as a particle accelerator, generating vast quantities of antimatter that are then flung out into the surrounding molecular clouds to die. However, there is a third, more exotic possibility, one that connects this mystery to the invisible skeleton of the universe. Some scientists speculate that the gamma rays could be the result of dark matter interactions. We know that dark matter makes up about 85% of the mass in the universe, and we believe it clumps densely in the centers of galaxies. While we do not know what dark matter is made of, leading theories suggest it is composed of WIMPs, weakly interacting massive particles. In many theoretical models, WIMPs are their own antiparticles. This means that if two dark matter particles collide, they can annihilate each other, releasing a cascade of energy that eventually decays into electrons and positrons. These positrons would then annihilate with normal matter, producing the gamma rays we detect. If this theory is correct, the glow at the center of the Milky Way is not just a light show. It is the first direct evidence of dark matter revealing itself. It would mean we are watching the invisible universe slowly burn. However, distinguishing between these theories is difficult. The galactic center is a messy, noisy place. It is crowded with supernova remnants, hot gas, and magnetic filaments. Finding the fingerprint of dark matter amidst the noise of thousands of dying stars is like trying to hear a whisper in a thunderstorm. Adding to the complexity is the question of symmetry. In the moments after the Big Bang, scientists believe matter and antimatter were created in equal amounts. Yet, today, the universe is almost entirely matter. If they had remained equal, they would have annihilated each other completely, leaving nothing but light. Somehow, matter won. The pockets of antimatter we see today in the galactic center are just tiny, local factories, not leftovers from the beginning. Understanding these local sources might help us understand the fundamental physics of why we exist at all. Despite decades of analysis, no single explanation has fully satisfied the data. The pulsar theory fits well, but the distribution of the signal, how spread out it is, doesn't perfectly match where we think the pulsars should be. The dark matter theory is mathematically beautiful, but relies on particles we haven't yet proven to exist. The center of the Milky Way remains a riddle wrapped in high-energy radiation. It forces us to look at the empty spaces between the stars and realize they are seething with invisible conflicts, where matter and antimatter wage a silent war, signaling their existence only through the ghost light of gamma rays. The universe, as we observe it today, is overwhelmingly composed of matter. Protons, neutrons, and electrons make up the stars, the planets, and ourselves. This presents a fundamental cosmological problem known as baryon asymmetry. According to our models of the Big Bang, the birth of the universe should have produced equal amounts of matter and antimatter. Since these two substances annihilate upon contact, a perfectly symmetrical universe would have instantly destroyed itself, leaving behind nothing but a sea of radiation. Clearly, that did not happen. Somehow, matter won the war, and antimatter became a rare ghost in the machine. The reasons for this survival are still unknown, making the detection of significant antimatter production in the heart of our galaxy a potential key to unlocking our own origins. Additionally, the possibility that dark matter could be involved in these gamma ray emissions raises stakes even higher. If the signal from the galactic center is indeed coming from the annihilation of dark matter particles, specifically the theoretical WIMPs, or weakly interacting massive particles, it would represent a historic breakthrough. It would mean that dark matter is not just dead weight holding galaxies together, but an active participant in particle physics that can be detected through its own destruction. Such a discovery would provide critical insights into the fundamental nature of this invisible substance, which remains one of the most elusive components of the universe. The center of our galaxy is a place of extremes: extreme gravity, extreme density, and extreme energy. It is a region where the usual rules of astrophysics often give way to more exotic processes. The presence of vigorous antimatter annihilation adds to the sense that this region is a laboratory for physics that we cannot replicate on Earth. Whether the gamma rays are the result of thousands of spinning pulsars, the violent dining habits of a supermassive black hole, or the self-destruction of dark matter, they offer a window into the most energetic and dynamic parts of the Milky Way. From the high-energy mysteries of the galactic core, we turn our attention to the quieter, more familiar corners of the universe, the star clusters. But even here, in the nursing homes of the galaxy, there are rebels that refuse to follow the rules of time. In the quiet, aging star clusters scattered throughout the universe, the stars follow a predictable life cycle. These clusters are like cosmic time capsules. All the stars within them were born at roughly the same time, from the same cloud of gas, because massive stars burn through their fuel quickly, and smaller stars burn slowly. Astronomers can estimate the age of a cluster by looking at which stars are still alive. In an ancient cluster, all the massive, hot, blue stars should have died out long ago, exploding as supernovae or fading into white dwarfs. The only survivors should be the smaller, cooler, yellow and red stars. But among these older populations, astronomers have noticed something strange. There are a few stars that seem completely out of place. These stars, known as blue stragglers, shine brightly with a hot, intense blue light that suggests they are young, massive, and vigorous. Their presence in these old star clusters poses a deep mystery. Finding a massive blue star in a 10-billion-year-old cluster is like walking into a retirement home and finding a teenager living among the residents. They simply should not be there. Blue stragglers are so named because on the Hertzsprung-Russell diagram, the graph astronomers use to plot the life stages of stars they appear to straggle behind in the aging process. While their siblings have evolved off the main sequence to become red giants, these stars have stayed behind, maintaining the heat and color of youth. They seem to defy the natural progression of stellar aging, as if they have somehow managed to rewind the clock. The question that has puzzled astronomers since their discovery by Alan Sandage in the 1950s is, how did these stars cheat death? Since stars cannot spontaneously generate new fuel out of nothing, the answer must lie in theft or violence. The prevailing theory to explain the existence of blue stragglers is that they are the result of stellar collisions or mergers. In this scenario, the star is not actually young. It is a born-again star, created from the combined mass of two older objects. When an old star gains new mass, its core is compressed, heating up and reigniting nuclear fusion with renewed vigor. This process effectively rejuvenates the star, making it hotter, brighter, and bluer, giving it a second lease on life. There are two primary ways this rejuvenation can happen. The first is a slow, parasitic process known as mass transfer. This typically occurs in a binary system where two stars orbit each other closely. As the stars age, one of them, usually the slightly more massive one, will evolve first, expanding into a red giant. As it swells, its outer layers of gas cross the gravitational boundary, known as the Roche lobe. Once the gas crosses this line, it falls onto the companion star. Think of it as cosmic vampirism. The smaller companion star siphons hydrogen fuel from its bloated neighbor. As it accumulates this fresh fuel, it gains mass. The extra mass squeezes its core, increasing the temperature and pressure, causing it to burn hotter and turn blue. The result is a blue straggler that looks young and massive, masking its true age. The donor star, having been stripped of its envelope, often fades away to become a dim white dwarf, leaving the thief to shine brightly. The second mechanism is far more violent, a direct physical collision. This is more likely to happen in the crowded environments of globular clusters, where hundreds of thousands of stars are packed into a relatively small volume. In these dense swarms, the average distance between stars can be much smaller than in the solar neighborhood. Occasionally, two stars will physically crash into each other. Rather than shattering like billiard balls, stars are fluid. They merge. The two smaller stars coalesce into a single massive object. The mixing of their fuel supplies and the intense heat of the collision create a new, rapidly spinning star that mimics the appearance of a young, massive star. Both of these mechanisms, mass transfer and stellar collisions, provide plausible explanations for the formation of blue stragglers, and it is likely that both processes occur in nature. However, they are not without their challenges. For one, not all blue stragglers seem to fit neatly into these categories. In some cases, astronomers have found blue stragglers that do not appear to be part of binary systems, and they do not show the rapid rotation expected from a collision merger. This raises questions about whether there are other, subtler ways a star can rejuvenate that we have not yet modeled. Additionally, while stellar collisions are more likely in dense clusters, space is vast, and direct hits are still statistically rare events. It is unclear whether collisions alone can account for the sheer number of blue stragglers observed in some regions. To solve this, astronomers have turned their most sophisticated tools, including the Hubble Space Telescope, toward targets like Messier 3. M3 is a globular cluster located about 33,900 light-years from Earth. It contains 500,000 stars packed into a ball of light. It is one of the premier laboratories for studying these objects. In M3, astronomers have mapped the positions of blue stragglers and found that they tend to sink toward the center of the cluster. This is due to a process called dynamical friction. Because blue stragglers are more massive than the average star in the cluster, gravity pulls them inward, while lighter stars drift outward. This segregation confirms that they are indeed heavier than their neighbors, supporting the idea that they are formed by combining mass. Interestingly, blue stragglers have also been found in open star clusters and even in the galactic field, the sparse regions of the galaxy where stars are spread far apart. The discovery of blue stragglers in these lonely environments complicates the picture. In the emptiness of the field, the chance of a random collision is virtually zero. This suggests that for these isolated stragglers, the mass transfer mechanism in binary systems must be the dominant cause. It implies that binary interactions are a fundamental driver of stellar evolution, capable of altering the fate of stars even in the quietest corners of the galaxy. The study of blue stragglers does more than just explain a few odd stars. It touches on broader questions about the nature of stellar evolution. In many ways, these stars represent the idea that stellar life is not always a linear path from birth to death. While most stars follow a well-understood sequence, blue stragglers show that the universe allows for exceptions. Stars can be rejuvenated, reborn, and altered by their environment. They demonstrate that gravity is not just a force that holds things together, but an engine of transformation that can breathe new life into dying worlds. From the manipulation of a star's lifespan, we descend to the fundamental fabric that allows age to exist at all. We move from the scale of light years to a scale so small it defies imagination. In the realm of physics, time is something we tend to think of as a continuous, ever-flowing river. We measure it in seconds, minutes, and hours. and we structure our entire understanding of the universe around its smooth passage. But when you delve into the deepest levels of theoretical physics, down to the very fabric of space and time itself, there exists a concept so abstract and removed from everyday experience that it challenges our understanding of what time really is. This is the concept of Planck time, named after the physicist Max Planck, who founded quantum theory. It is considered the smallest possible unit of time. It is not just a very short amount of time, it is a fundamental limit. In our macroscopic world, we can always divide a second into smaller halves, milliseconds, microseconds, nanoseconds. But quantum mechanics suggests that this division cannot go on forever. Eventually, you hit a bedrock, a pixel size for the universe. Planck time is approximately 10 to the power of negative 44 seconds. To try and visualize this, consider the blink of an eye. In the time it takes you to blink, more units of Planck time have passed than the number of seconds that have ticked by since the Big Bang. It is the time it takes for a photon of light to travel a distance equal to the Planck length, which is itself the smallest possible unit of distance. Why does this limit exist? It arises because, at this unimaginably small scale, the laws of physics as we know them break down. The smooth geometry of Einstein's general relativity, which describes gravity and space-time, crashes into the probabilistic, jittery world of quantum mechanics. Below the Planck scale, the concept of before and after may cease to have meaning. Space-time itself may become a frothing, chaotic foam where cause and effect are no longer linear. This suggests that time is not a smooth, continuous flow like water, but rather something discrete, like the frames of a movie reel. We perceive motion as smooth only because the frames are moving too fast for us to see the gaps. If this theory is correct, then the universe is clicking forward, one Planck moment at a time. The existence of such a limit implies that the universe is granular at its core. It challenges our understanding of what time really is. This theoretical boundary is known as Planck time. It is the smallest possible unit of time that can physically exist, a fleeting moment so brief that it resides far beyond the reach of our machines to measure or our minds to truly visualize. To understand Planck time is to stand at the very edge of reality, looking over the precipice where the known laws of physics crumble into uncertainty. The concept bears the name of the German physicist Max Planck, one of the intellectual giants of the early 20th century and the father of quantum theory. Planck was driven by a desire to strip away the arbitrariness of human measurement. He realized that units like the second or the meter were historical accidents based on the rotation of the Earth or the length of a platinum bar in Paris. If we were to meet an alien civilization, their seconds and meters would be completely different from ours. Planck sought something deeper, a system of measurement based solely on the immutable constants of nature, the speed of light, the gravitational constant, and the quantum of action. From this work, he derived a set of natural units, including Planck length, Planck energy, and Planck time. These are not merely mathematical curiosities. They represent the hard limits of the universe's resolution. To grasp just how small Planck time is, we must stretch our imagination to the breaking point. 1 unit of Planck time is approximately 5.39 times 10 to the power of negative 44 seconds. Written out, that is a decimal point, followed by 43 zeros, and then a 5. This number is so minuscule that analogies almost fail us. Consider the time it takes for you to blink your eye. In that fraction of a second, more units of Planck time have passed than the number of seconds that have ticked by since the Big Bang began 13.8 billion years ago. It is defined physically as the amount of time it takes for light, the fastest signal in the universe, to travel a distance of 1 Planck length. 1 Planck length is about 1.6 times 10 to the power of -35 meters. If you were to magnify a single atom until it was the size of the entire observable universe, a Planck length would, on that scale, be the size of a single tree. Why does this specific number matter? Why can't we just divide time into smaller and smaller pieces forever? The answer lies in the conflict between the two pillars of modern physics, general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes space and time as a smooth, continuous fabric, like a sheet of rubber that stretches and curves. Quantum mechanics, however, describes the world of particles as discrete, jittery, and pixelated. At the scale of Planck time, these two theories crash into each other. If you try to measure a duration shorter than Planck time, the energy required to make that measurement would be so concentrated that it would collapse the tiny region you are looking at into a microscopic black hole. Thus, the measurement becomes impossible. Below this threshold, the very concepts of before and after cease to have meaning. The smooth fabric of Einstein's space-time tears apart, replaced by what physicists call quantum foam. In this regime, the universe is no longer a stable stage where events play out. Instead, space and time themselves are churning, boiling, and fluctuating. Geometry becomes turbulence. Wormholes may open and close spontaneously. Dimensions may curl up and unfold. It is a world of pure probability, where the familiar rules of cause and effect dissolve. This is why Planck time is often called the pixel size of the universe. Just as a digital image is made of pixels and contains no information smaller than a single dot, the universe may be constructed of discrete units of space-time, with nothing existing in between. The implications of this are profound when we look backward to the origin of all things. According to the Big Bang Theory, the universe began as an infinitely hot, dense point that expanded rapidly. But if we try to rewind the cosmic movie all the way back to the distinct moment of zero, we hit a wall. That wall is the Planck era. Physicists believe that for the first interval of time, from 0 to 1 unit of Planck time, the universe was in a state that our current physics cannot describe. During this brief epoch, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were likely unified into a single superforce. In this environment, gravity was as strong as the other forces, and quantum effects ruled the structure of space-time itself. Because we do not yet have a theory of quantum gravity that unites the smooth world of relativity with the pixelated world of quantum mechanics, the Planck era remains an opaque curtain drawn across the birth of the universe. We can speculate, but we cannot know. This leads us to a philosophical precipice. If time has a minimum unit, does that mean time is not a continuous flow, but a series of jumps? In our everyday experience, time feels like a river, smooth and unbroken. But at the Planck scale, time might be more like a movie reel. A movie looks like continuous motion, but it is actually a series of static images shown in rapid succession. Between frame 1 and frame 2, there is a gap. If the universe operates on Planck time, are we living in a cosmic stop-motion animation? And if so, what happens in the gaps between the ticks of the universal clock? Does the universe simply cease to exist for an instant, only to reappear in the next Planck moment? Some physicists suggest that time might not be a fundamental component of reality at all. In this view, what we perceive as time is an emergent property, something that arises from the interaction of deeper, timeless quantum states, much like how heat emerges from the movement of atoms. An individual atom is not hot or cold. Heat only exists when you have a group of them moving together. Similarly, perhaps time only makes sense when you zoom out from the Planck scale. At the deepest level, the universe may be static and timeless, a vast equation where everything simply is. In classical physics, Isaac Newton viewed time as an absolute container, a clock that ticked at the same rate for everyone, everywhere, regardless of what was happening inside the container. Einstein shattered this idea, showing us that time is relative. It slows down near massive objects like black holes and stretches out for travelers moving at high speeds. Time became part of the physical fabric, dubbed space-time. But Planck time threatens to shatter our understanding once again. If space and time dissolve into quantum foam at the smallest scales, then the smooth space-time of Einstein is just an approximation, an illusion that holds true only for large, slow-moving creatures like us. It suggests that the continuum we rely on for our mathematics is a mirage. The quest to understand Planck time is really the quest for the holy grail of physics, the theory of everything. Scientists are searching for a framework, such as string theory or loop quantum gravity, that can describe the granular structure of space-time without breaking down. Until we find it, Planck time represents the absolute horizon of human knowledge. It is the point where our map of reality ends and the "here be dragons" of the quantum realm begins. We have journeyed from the vanishing phantom of the planet Fomalhaut B to the dark gravitational scaffolding of the Boötes void. We have watched stars being flung from the galaxy at hypervelocity speeds and peered into the impossible geometry of the red rectangle. We have questioned the stability of our own solar system and looked for the ghost light of antimatter in the galactic core. Finally, we have drilled down into the bedrock of reality itself, finding that even time has a limit. These phenomena, from the gargantuan to the microscopic, serve as reminders of the complexity of the cosmos. The universe is not merely a collection of stars and rocks. It is a dynamic, evolving, and often baffling machine, operating on rules we are only just beginning to decipher. It hides its secrets in the darkness of voids, in the blinding light of dying stars, and in the fleeting fractions of a second that make up the fabric of existence. We build telescopes to see farther and particle accelerators to look deeper, driven by an insatiable curiosity to understand our place in this vast mechanism. Each discovery answers one question, but asks 10 more. Is the universe made of discrete pixels? Are there other universes leaving bruises on our own? Do planets wander the dark forever, teeming with life beneath the ice? The answers await us in the data, in the light of distant stars, and in the theoretical equations yet to be written. For now, we stand on our small planet, looking up and looking in, witnessing the unfolding mystery of a universe that is far stranger and far more beautiful than we ever dared to imagine.